Hey, hi, good evening. Welcome to the class. So, today's class is about quantization. So, today's class is about quantization. Hey, hi, welcome to the class. Good evening and welcome to the class. Right. Hey, hi, welcome to the class. Good evening and welcome to the class. Right. So, today's topic is quantization. So, here I'm assuming few things here. So, because this class is about a discussion of previous year questions, a little tricky previous year questions on quantization topic. So, I'm not discussing every single concept of quantization here, but here I'm discussing the tough part of quantization. So, what I'm assuming is you know little bit about quantization. What is quantization? You should be knowing. To understand this class, basics of quantization you should be knowing, right? So let me quickly recollect what is quantization. Quantization means it's like converting infinite possible voltages into finite possible voltages. So if the message is having voltages from -4 delta to +4 delta. So here if you observe this quantizer characteristics if you observe, yeah, so this is a 3-bit quantizer. This is a 3-bit quantizer. So this is a 3-bit quantizer. Why am I saying it is a 3-bit quantizer? Because this is having eight quantization levels: 1, 2, 3, 4, 5, 6, 7, 8. Because it is having 8 quantization levels, I am calling it as a 3-bit quantizer. Number of bits used by a quantizer can be any number of bits. Because for me, it is easy to it is easy to plot a 3-bit quantizer characteristics. That's why I've plotted 3-bit quantizer characteristics. But practically, we may be using 8 bits. Okay, practically we may be using 8-bit quantizer, which means 2 to the power of 8, which means 256 quantization levels will be used. But in this example that I'm showing you, I'm plotting a 3-bit quantizer characteristics, which means 8 quantization level characteristics. So since 8 quantization levels are there, so the total voltages occupied by the signal are divided into 8 regions. Are divided into 8 regions because we are allowed to have 8 quantization levels. That's why we are allowed to divide the voltage swing of the signal into 8 different regions. Each region we call it as quantization region, and the midpoint of each in the midpoint of each quantization region we call it as quantization level. So for example, if let's say message signal m of t takes voltages 4 cos 1000 pi t. For example, this is the message signal. Okay, so now this message signal takes voltages from -4 to +4 volts. Okay, so the total voltage swing is how much? Voltage swing is 8 volts. And how about the step size? Step size formula is voltage swing divided by 2 to the power of n. What is n here? 3 bits. So step size is equal to 1 volt. So here step size is 1 volt and number of quantization levels can be, number of quantization levels L is 2 power 3, which is equal to 8. Which means total voltage possible from -4 to +4 is divided it into 8 regions or 8 parts. So each part is of size 1 volt. Okay. So I'm just taking an example for you to understand it better. So the total, all the voltages from -4 to +4 are divided into 8 parts. Each part is what we call a step size. and minus 4 delta to plus 4 delta, this is first quantization region, second quantization region, and so on. Like that, 8 quantization regions are there because 8 quantization levels are allowed. And in every quantization region, this 4 minus 4 delta is one quantization boundary. This minus 3 delta is also a quantization boundary. Minus 2 delta is also quantization boundary. In every quantization region, first region, second region, third region, in every region there will be two boundaries, and they are quantization boundaries. In questions, they will be mentioning this word quantization boundaries, which means they are talking about these voltages: minus 4 delta, minus 3 delta, minus 2 delta, and so on. So generally, the midpoint of these quantization boundaries is taken as quantization level. So what is the midpoint of these two boundaries? It is minus 3.5 delta. Yes, this is one quantization level. And what is the midpoint of these two boundaries? It is minus 2.5 delta. The midpoint of these two boundaries is minus 2.5 delta, 1.5 delta, and 0.5 delta, minus 0.5 delta. Similarly, 0 to delta midpoint is 0.5 delta, 1.5 delta, 2.5 delta, and 3.5 delta. So these are the quantization levels. The meaning of quantizer is, if you give an input with voltage which is between 0 to delta, which is between 0 to delta, the output of the quantizer will be delta by 2. If you give an input which is between delta to 2 delta, the output of the quantizer will be 3 delta by 2. Similarly, you can understand for other voltages. So at the output of the quantizer, only discrete voltages are possible. For example, in this quantizer, if this is the quantizer characteristics, at the output of quantizer, input of quantizer can be any voltage from minus 4 delta to plus 4 delta. But output of the quantizer will be definitely 7 delta by 2 or 5 delta by 2 or 3 delta by 2, delta by 2, minus delta by 2, minus 3 delta by 2, minus 5 delta by 2, and minus 7 delta by 2. So this is the quantizer characteristics, input versus output characteristics. Now if you observe these characteristics, this is input to the quantizer versus quantization error characteristics. If you can plot, since you know x versus y characteristics, you can plot x versus x minus y characteristics. It is going to look like this. Now this is quantization error. Whenever you are doing quantization, we have some problem called quantization error. So what is this quantization error? You should understand. So the input to the quantizer is some voltage, and the output of the quantizer is an approximation of the input voltage. If you are doing approximation, there is some small amount of error, and that error is what we call as quantization error. And our target in the design of quantizer always should be to minimize this error. We have to design it in such a manner that the error is minimum, right? So if you observe the errors, the error is always from quantization error is always ranging from minus delta by 2 to plus delta by 2. The error is always ranging from minus delta by 2 to plus delta by 2. So you can see this. In this region from 0 to delta, error is ranging from minus delta by 2 to plus delta by 2. Similarly, in this region also, it is same thing is happening. In every region, the same thing is happening. Error always goes from minus delta by 2 to plus delta by 2. And the maximum quantization error is how much? It is only delta by 2, right? Now, since I have just quickly recollected the basics of quantization, I've fastly recollected the basics of quantization. Now, let me talk about the most important thing and little tricky part here, which is signal to quantization noise ratio. If there is any tough question asked on quantization, that definitely will be on this signal to quantization noise ratio. So once I derive this formula for SQNR, I'll talk about different possible problems, and I'll talk about some previous questions also. Here I'm having some 3 or 4 previous questions, which are little tricky questions, and those questions I'll be solving for you. Right. Now let us derive SQNR. So whenever you are passing a signal through a quantizer, so for example, this is the flow, basically sampler, quantizer, and encoder. Your message signal is sampled, and samples of the signal are here, and these samples are quantized, and quantized means simply approximating, you can say, and these are finally converted into bits. So this signal is quantized, and whenever it is quantized, we get some quantization error, which is equal to input voltage minus output voltage. Input voltage is m of NTS minus output voltage is m cap of NTS. Or in this language, in the graph, whatever language we have used, if you use the same language, it is x minus y. Input voltage to the quantizer minus output of the quantizer. Right. So this quantization error, you can just think of it as noise. Because noise means any unwanted voltage, we call it as noise. our message signal voltage is little different from the quantized voltage. So which means there is some small difference between the actual voltage and quantized voltage. And this is what we call as quantization error. And quantization error, we can also call it as quantization noise also. Okay, whenever there is noise or whenever there is an error, there is a parameter to measure the quality. So because of this quantization error, definitely quality is reduced. And how much is that reduced? We can measure very well using SQNR. SQNR means signal to quantization noise ratio. For a normal noise also, because of noise, quality reduces. And how much is the quality reduced because of noise? We measure using a parameter called SNR, signal to noise ratio. Similar to SNR, here we are measuring signal to quantization noise ratio. So what is the formula for signal to quantization noise ratio? It is simply signal power divided by quantization noise power. Here, to understand the quality reduction due to quantization error, we are trying to find SQNR. And many questions can be asked based on this SQNR. So SQNR is not signal it's not signal voltage by quantization voltage. It's a signal power divided by quantization noise power. Right. Now, let us calculate the formula for SQNR. To calculate the formula for SQNR, first of all, we should assume few things. First, let me make the first assumption. And at the end of this derivation, I'll tell you for different cases how will the formula change. So first of all, let me assume something. So let me assume the message as AM cos omega mt, which means I'm assuming the message to be a sinusoidal signal. Okay, because practical signal need not be sinusoidal signal, but I am assuming some signal just for the calculation sake. So if the message changes, definitely our calculation final answer also changes. But let us do the calculation for this signal. Now, one more thing, we also have to understand about quantization error also. Fine. First, let us understand the signal power, because signal is given. We can clearly understand the signal power. And how much is the signal power? Signal power is equal to AM square divided by 2. You should be knowing what is the signal power of a sinusoidal signal. It is peak amplitude whole square divided by 2. Yes, now we are clear with first one part, which is signal power. Second thing. So how about quantization noise power? We want to understand quantization noise power. Quantization error, or quantization error means quantization voltage. Quantization noise voltage. This is voltage. This varies from minus delta by 2 to plus delta by 2. And this quantization error voltage, is it a deterministic value or a random value? It is definitely a random value. It is definitely a random value. It's a random value, right? Because we don't know at any point of time what will be the error. Error can be anywhere in this range, right? So now what we want to find is quantization noise power, or simply average quantization noise power. Nobody says average, but exactly speaking, it is average quantization noise power. Average quantization noise power, how can you find it? Whenever you want to find the power of a random signal or a random voltage, how do you find it? We find it using expectation of x square, or in this case quantization error is taken as QE. QE is squared means error is this random variable. Quantization error is a random variable. So random variable square and expectation. This value will give you always mean square value. Mean square value. Mean square value always will give you power. So quantization error is a voltage, and voltage is squared. It represents power. Expectation of power will give you average power. So here we are going to get average quantization noise power. This is the formula that I am using because quantization error is a random value. If it was a deterministic value, then I would have used this formula, integration of modulus of QE square, integration from minus infinity to, minus 0 to t, 1 by t, something like this. This is the formula for power. This kind of formula I would have used if I'm talking about a deterministic signal. But since I'm talking about random signal, always whenever you're talking, let's say if x is a random signal, so power in x is simply, we can find it by using this formula, expectation of x square. This is how we find the power in x square. Or we also simply call this as mean square value. This is the way to find the power in any random signal, right? So I have given you the formula of how to find the power in any random signal. Similarly, quantization error is a random signal, so this is how you have to find the power in quantization error. Now, if you want to find expectation, you know the formula for expectation, right? So the formula for expectation is integration of what is inside value, same thing, copy it, QE square into what is the random variable here, QE is the random variable, so multiply with PDF of QE and integrate with respect to QE only. So you'll write the formula for, let me recollect the formula that you know. It is integration of x square into fx of x dx. This is the formula that we write, right? So limits from minus infinity to plus infinity. So this is the basic formula for expectation of x square. Instead of x, we are having QE. So I'm just replacing everywhere, wherever x is there, I'm replacing it with QE. Right. So this is the formula. Now, if you want to find this average quantization noise bar, first of all, you should know what is the PDF, right? So let us assume this also. Here we are assuming quantization error to be having uniform PDF. Uniform probability density function, because we don't know what is the PDF of quantization error. So we are making one more assumption here. So till now we have made two assumptions. One is message is sinusoidal, we have assumed. Second thing is quantization error need not be having uniform PDF, but we are assuming it to be uniform PDF, and we are doing the derivation. Okay, so under these two assumptions only, whatever answer we are going to get, that is valid. In other cases, the answer will change a little bit, and what are those changes, I tell you. Right, average quantization noise bar formula we have written. So since we have assumed it to be uniform PDF, let me draw the PDF. Of quantization error as a function of QE. I am plotting FQE of QE. So we know it takes values from minus delta by 2 to plus delta by 2, minus delta by 2 to plus delta by 2. So the height should be 1 by delta, because this is PDF and area of PDF should be 1. That's why I'm taking the height as 1 by delta. And when they're saying uniform PDF, what that means is whatever values quantization error takes, all those values will have same probability. That is the meaning of uniform PDF. Right, now we know the PDF. Let us calculate this. So expectation of QE square is equal to integration of QE square into, what is the equation for FQE of QE? Let me write the equation for this. It is equal to 1 by delta for minus delta by 2 less than QE less than delta by 2. This is the equation. It is equal to 0 elsewhere. Let us substitute this equation here. So it is equal to 1 by delta. In place of FQE of QE, I am substituting 1 by delta, and this substitution of 1 by delta is valid only from minus delta by 2 to plus delta by 2. And now let us integrate 1 by delta outside. And what is integration of QE square? It is QE cube divided by 3. It is as simple as integrating x square. Integration of x square is x cube by 3. Instead of x, we are having QE. Limits are from minus delta by 2 to plus delta by 2. So this is equal to 1 by 3 delta outside. And let us substitute the limits. Upper limit, if you substitute, it is delta cube divided by 8 minus of minus delta cube divided by 8. I am substituted upper limit and then lower limit and subtracted. So this is equal to del square, because one delta is cancelled, and here this becomes 2 times delta cube by 8, which is delta cube by 4. 4 into 3 is 12. So finally the answer is del square by 12. So finally, quantization noise bar or average quantization noise bar formula is del square by 12, and this is the formula which is valid only under the assumption that quantization error is having uniform PDF. Okay, and this formula, under what conditions this formula is valid? Whenever somebody says quantization error is having uniform PDF, or the same thing they'll say in a different manner. So what are the ways in which they can say the answer? Say the same thing. In what situations you can use this formula? Let me tell you. If nothing is mentioned, for example, if no information about message, first case is if no information about message, then you can use quantization noise bar formula as del square by 12. And second thing, if sinusoidal message then also you can assume quantization noise power to be del square divided by 12. Next, third case, if uniform PDF, if message is having uniform PDF, if message is having uniform PDF, then also you can say quantization noise power is del square by 12. Okay, here no information means by default you can assume. There is nothing wrong in assuming whenever message information is not given or whenever message is said to be sinusoidal, then under those conditions you can assume the quantization noise power to be del square by 12. There is no problem. Similarly, whenever message is having uniform PDF, so whenever message is having uniform PDF, in that case, you just observe this. Whenever message is having uniform PDF, which means when the message is having same probability for all voltages, then definitely quantization error also will have same probability for all the voltages from minus delta by 2 to plus delta by 2. So perfectly speaking, whenever message is having uniform PDF, perfectly quantization error is also going to have uniform PDF. Whenever message is having uniform PDF, quantization error also will have uniform PDF. But when message is having a triangular PDF, then definitely we cannot say quantization error is having uniform PDF. And when message is having a different PDF other than uniform PDF, then quantization error is not going to be having uniform PDF. Then this formula is not valid. Right? This formula del square by 12 is valid under these three situations. Under these three situations, you can use this formula. If the situation is different other than these three, then you cannot use this formula. You have to go with some other procedure. Okay, that some other procedure I will not be able to discuss in this class. So maybe in some other class we will discuss. Okay, because time will not be sufficient, so I will not be able to discuss to that level. Right. So we have understood quantization noise power. Now let us calculate SQNR. Signal to quantization noise ratio is equal to, what is the signal to quantization noise ratio? Just now we have calculated the signal power and quantization noise power. AM square by 2, signal power divided by quantization noise power, divided by quantization noise power. And signal power is AM square divided by 2. That is what we got, because we have assumed the message is sinusoidal. If message is different other than sinusoidal, this power will change. Next, quantization noise power, under these three situations it is del square by 12. So this is equal to AM square divided by 12 into the numerator, 12 divided by 2. So here in the denominator it is del square. So step size can be written as, what is the formula for step size? It is voltage swing. The formula for step size is voltage swing divided by 2 to the power of n. And what is the voltage swing in this case? Since the message is AM cos omega mt, highest voltage possible is AM and lowest voltage possible is minus AM. So voltage swing is 2 times peak amplitude of the sinusoidal signal. 2 AM is the voltage swing divided by 2 to the power of n. So let me substitute in place of delta, 2 AM divided by 2 to the power of n whole square. 2 ones, 2 6. AM square cancelled. So finally SQNR is equal to, so in the numerator it is 6 and in the denominator it is 4. 2 cancelled, it becomes 3 by 2. 2 is cancelled here and here. Now what is left is 3 by 2, and this 2 power n whole square is 2 power 2n into the numerator. It becomes 2 to the power of 2n. So finally this formula is 3 by 2 times 4 to the power of n. And what conditions this formula is valid? Whenever you assume the message to be sinusoidal, and whenever you assume the quantization noise power to be del square by 12, under these situations only, under these assumptions only, quantization noise power formula is 3 by 2 into 4 power n. And the same formula, whenever you are talking about SNR, always if you observe the answers for SNR, it will be in dB scale. So it makes sense to talk about dB scale for SNRs or SQNRs. So mostly our answers for SQNR will be in dB scale only. So that's why let us convert this into dB scale. So this is equal to 10 log, same answer in dB scale, 3 by 2 into 4 to the power of n, which is equal to 10 log 3 by 2 plus 10 log 4 power n to the base 10. So which is equal to, So you have to use 10 log whenever you are applying a logarithm for second order values like power ratios or energy ratios. You have to use 10 log formula. If you are using if you are applying the logarithms, or if you are trying to find the dB values, dB scale values for first order signals like voltage, current, then you have to use 20 log. Whenever you're dealing with second order terms like energy and power, use 10 log. Whenever you're dealing with terms like voltage and current, then use 20 log. Right, this is equal to 10 log 3 by 2. If you use the calculator and calculate, it becomes 1.8 dB plus. So n into the n comes here, it becomes n times 10 log 4 to the base 10. So this is equal to 1.8 plus. So 10 log 4 to the base 10 is 0.6. 0.6 into 10 is 6. This becomes 6n. So finally, we got some really important result, and that result is, it is 3 by 2 into 4 to the power of n, or same thing, same answer in dB scale is 6n plus 1.8 dB. Very powerful answer, very important result. Questions can be asked based on this result. Okay, so whenever now this is the formula that you can use by default whenever there is no clarity about message, or if it is sinusoidal message. Under these two situations you can use this formula. When the message is having uniform PDF, and if message is having uniform PDF, then the formula will change a little bit. Okay, why? Because signal power will change. If the message is having uniform PDF, then definitely quantization noise power will not change, it is del square by 12 only, but signal power will change. And when message is having uniform PDF, just observe carefully, when message is having uniform PDF, so message has uniform PDF, which means it takes voltages from minus AM to plus AM as a function of x, fx of x. If they say, somebody says message is having uniform PDF, and what is the height? It is going to be 1 by 2 AM. Now, if you want to find the signal power, how do you find the signal power for message? Signal power. If the message is having uniform PDF, then signal power is equal to, how do you find this? Expectation of x square. And if you find expectation of x square for this one, it will turn out to be AM square divided by 3. You can use the formula that we have used, integration of x square into fx of x dx. If you use that, you'll be getting AM square by 3. Right. So if the message is having uniform PDF, then signal power is AM square by 3. Then substitute AM square by 3 in place of AM square, in place of signal power. It will be AM square by 3 here, by 3 here, by 3 here, which means 3 gets cancelled. It will become only 4 to the power of n. So if message is having uniform PDF, then definitely quantization error also is having uniform PDF. So the quantization noise power is same, which is del square by 12. Now what happens to the answer? Let us see. Signal power has changed from AM square by 2 to AM square by 3. Now in place of 2, you are having 3. In place of 2, you are having 3. So what happens is, this 2 will not get cancelled. Okay, 3 will be there in the denominator. So 3 gets cancelled. So the answer will be SQNR is equal to 4 to the power of n. If you apply 10 log to this one, it becomes 6n dB. This is the answer. If whenever anybody says message signal is having uniform PDF, under this condition, this is the answer. If they say message is sinusoidal, then this is the answer. In some other situation, when there is no clarity on the message, what happens is signal power, when it changes, for example, if you are talking about some other signal, then the formula may be AM square by 4 or AM square by 5. This value will change. Because of this value, what happens is, the constant here, instead of 3 by 2, we may be having different constant. So this constant part will change, which means this constant part, in place of 1.8 dB, here it has become 0 dB. For some other signal, it becomes some other dB. But 6n is common. 6n is common for any signal. So for any signal, definitely 6n part will be common for any message signal. Given any information, 6n will be common. Right. So finally, the conclusion is, mostly SQNR values are proportional to 6n dB. Okay. So if anybody says, for example, a signal to quantization noise ratio is 49 dB, and 49 dB, what is the closest value of 6n to 49? 8 6 are 48. Okay, which means n, for n equal to 8, so 6n is 48. So they have given 49. So even if they have given 49 or 49.8 or 48 exactly, it doesn't matter. What is the closest multiple of 6 we are having? Okay, if they are saying 43 for example, so 43, what is the closest multiple of 6 which is closest to 43? Which it is 42. 42 means 6 sevens are 42, which means n is 7 bits. So from whatever SQNR they are giving you, the most important thing that we need to find out is the n value, the number of bits. Okay, so if you can figure out the n value, you can solve the problem that they are asking you. Okay, I hope I have given you clarity on these SQNRs. So this is the formula for message uniform PDF. This is the formula for when message is sinusoidal. Okay, if it is some other message, then the answer may not be 6n or 6n plus 1.8. It will be something close to 6n. Okay, for example, n is 6 bits. Then 6 is 36 dB. So they may not give you 36 dB exactly. They may give you 1 or 2 dB this way or that way from 36 dB. Maybe like 35 dB or 37 dB or 38 dB, something like that. If they give you, you should understand what is the closest multiple of 6 for that. So once you understand what is the closest multiple of 6 correspond to that dB, then definitely you can understand the number of bits. If you can understand the number of bits, then you can solve the whatever question they are asking you. Right. Now, let us get to the problems. So I am going to talk about problems which are completely not formula based. So there will be many problems that will be asked based on these formulas only. Whatever formulas I have given you here, based on these formulas, a lot of problems can be solved very easily. But I am going to solve questions which are a little different. Whenever such questions are given, you have to go with the basics, which means what is the basic procedure that we have taken to solve to get this SQNR derivation. That basics you have to go through. The same procedure you can go through for any problem which is little different from regular problem. Okay, so we'll talk about that. So I'll tell you one basic question that is possible here. So for example, if you see the formula for delta, the formula for delta is voltage swing divided by 2 power n. So delta is proportional to 1 by 2 to the power of n. Similarly, quantization error is equal to delta by 2, which means quantization error is also proportional to 1 by 2 power n. And quantization noise bar is proportional to, you can see, quantization noise bar is proportional to del square. Since del is proportional to 1 by 2 power n, quantization noise bar is proportional to 1 by 4 to the power of n. And SQNR is proportional to 4 to the power of n, or it is proportional to 6n dB. Okay, based on this, lot of questions can be asked, lot of interesting questions can be asked. So I'll tell you one question. If n is increased, by 1 bit, like for example 6 bits to 7 bits, they have increased from 6 to 7 or 8 to 9, something like that, 1 bit they are increasing. What happens if they increase the n value by 1 bit? So what happens to step size? If they increase n by 1 bit, then what happens is step size changes by 1 by 2 times. Delta changes by half times, or the same answer can be told like this: delta decreases by 2 times. Same question can be asked like this or like this. It changes by how many times or decreases by how many times. Similarly, quantization error also exactly same answer. Quantization error also changes by half times or decreases by 2 times. Next, how about quantization noise bar? Quantization noise bar decreases by 4 times, or it changes by 1 by 4 times. Okay. Similarly, what else they can ask you? They can ask you about SQNR, right? So SQNR, since it is proportional to 4 power n, when n increases by 1 bit, so SQNR increases by 4 times. SQNR increases by 4 times, or they can also say changes by 4 times. Okay, or the other way of saying it is SQNR increases by, in dB scale, if they give you the answer, it increases by 6 dB. So for example, same questions, instead of 1 bit, I am making it 2 bits. If it is 2 bits, what happens here? Delta changes by 2 power 2 times, which means instead of 1 by 2, it becomes 1 by 4, and it decreases by 4 times. Similarly, quantization error also same answers, 1 by 4 times and 4 times. So here, quantization noise bar, it is proportional to 1 by 4 power n, 1 by 4 power 2, which is 1 by, it changes by 16 times, or it changes by 1 by 16 times, or it decreases by 16 times. Similarly, whatever is in blue is for 2 bits. So SQNR, what happens? SQNR increases by 16 times, and dB scale it increases by 12 dB. So they can ask you questions like this. They'll change the number of bits by 1 bit and what happens to each and every parameter. There are 4 parameters that they can ask you questions on: delta, step size, quantization error, quantization noise bar, and signal to quantization noise ratio. So these are the basic questions that can be asked, and the other basic questions can be asked based on the simple formulas. Now let us talk about the questions. The questions which are little different from the routine. Right. So let us solve this question. So the amplitude of a random signal is uniformly distributed from -5 to +5 volts. So if the SQNR required in uniformly quantizing the signal is 43.5 dB, then the step size of the quantization is approximately. They're asking about the step size, correct? So now, if you observe the signal to quantization noise ratio (SQNR), it is given as 43.5 dB. Actually, they have not given exactly correct value here, because they are saying random signal is uniformly distributed. If it is uniformly distributed, we know the exact answer. It should be 6n. So 6n means it should be a multiple of 6, nothing extra. So it means it should be exactly 42 dB. But they have given the question as 43.5 dB. It's a small mistake, I can say. But still, this is a previous question. Even though there is a small mistake also, not a problem. We can do the problem correctly. So actually, it should be 42 dB, because since they have given it is uniformly distributed signal, definitely the answer should be 6n only, which means 42 dB should have been given. But fine, even if it is 43.5 dB also. So tell me this, what is the n value? What could have been the n value? Even if it is 43.5 also, what is the closest multiple of 6 for this one? 42. If it is 42, if you're writing this as formula as 6n, then what is n value? N is 7 bits. Okay. Now, they're asking about step size. Step size is equal to voltage swing divided by 2 to the power of n. And voltage swing is how much? 5 is the highest voltage, lowest voltage is -5. So highest voltage minus lowest voltage will give you the voltage swing, which is 10 volts, divided by 2 to the power of 7. This is equal to 5 divided by 2 to the power of 6. Yeah, you can leave it like this. Okay. So this is the answer for step size of the quantization. And I think this turns out to be 0.078. This is the answer. Okay. Fine. Right. This is the answer. You can use the calculator to calculate it. Fine. So this is a routine question actually. There is not much tricky part in this question. It's an easy question only. But the only thing that here the confusion is 43.5, but it should have been 42 dB. But fine. Now let us talk about the second question. This is little confusing question. It is little tricky. Okay. Let us see the question. So if the positive values of the signal are uniformly quantized. So if the positive values of the signal are uniformly quantized with a step size of 0.5 volts, 0.05 volts, and the negative values are uniformly quantized with a step size of 0.1 volts, then the resulting signal to quantization noise ratio is, so they are asking about SQNR, correct? So it is equal to signal power divided by quantization noise bar. This is the basic, right? Since the question is little different, since they are taking different step sizes for positive voltages and negative voltages, this is a little different question. Whenever they give you a different question, you have to go with the basics. You have to go with the basic derivation only. So you cannot use any formula here, because the question is different from what we, under what conditions we have derived the formula. From that assumptions, it is little different. So that's why we have to go with the basics. So what is the signal power? Signal power is very easy to find, right? Signal power is very simple. What did they say about the signal? They said signal is uniformly distributed. Signal is uniformly distributed, and it takes voltages from -5 to +5. So what shall we do now? It is from -5 to +5 means for uniform signal we know the formula for it. It is its peak amplitude square divided by 3 you'll get, or else you go with the basics of expectation of x square. Signal power will be 5 square by 3. Signal power will be 5 square by 3 divided by quantization noise power is what we need to figure out. So how about quantization noise power for positive voltages? Because they are taking different step size for positive voltages and different step size for negative voltages. So let us calculate the quantization noise power for positive voltages and negative voltages differently. So for positive voltages, if you observe, for positive voltages, the step size is taken as 0.05. So what is the formula for quantization noise bar? Can we take this formula? Del square by 12? Yes, definitely we can take, because message is having a uniform PDF. So obviously quantization noise bar also, quantization error also will have uniform PDF. Whenever quantization error is having uniform PDF, you can use this formula del square by 12. For negative voltages also you can use the same formula del square by 12. But for positive voltage, the step size is taken as 0.05. So it is 0.05 whole square divided by 12. And for negative voltages, it is, what is the step size for negative voltages? It is 0.1. 0.1 whole square divided by 12. Now you should understand. So what is the average quantization noise bar for all voltages? For all voltages, average quantization noise bar only for positive voltages we got, only for negative voltages we got. For all voltages, it is nothing but the average of these two. And if you observe, what is the average? 0.05 whole square divided by 12 and 0.1 whole square divided by 12. And how do we average these values? So for positive voltages, what is the probability? It is half. And for negative voltages also, it is half. Whenever we want to average values which have probabilities, how do you do that? You just multiply the values which you want to average with their corresponding probabilities and then do addition. You'll be getting the average. Okay, it is very simple. So you can find this using the calculator. So once you find this, you substitute here, and you calculate the value, you'll get SQNR. And once you get the value, you convert that into dB scale. Once you convert that into dB scale, you'll get the required answer. So the answer may be something close to 40, it's not 46, I guess. It should be, I don't remember the exact answer. So you can calculate and apply 10 log to this one, you'll get the exact answer. Okay. This is how you have to solve whenever the question is little different. So earlier, what is the assumption we have taken? When we have solved that derivation, we have assumed that step size is same for all voltages, for positive and negative voltages, same step size. But here it is different, so we have to go with the basic derivation. Whatever the procedure in which we have done the derivation, same procedure you can take whenever the question is little different. Now let us do some other question. Yeah. Okay, let us solve this problem. So this is also a little different question. So peak to peak input to an 8-bit PCM encoder is 2 volts. They're talking about PCM system. PCM system means it's nothing but sampler, quantizer and encoder. All of them together we call it as a PCM system. Okay, to the PCM system input, it's 8-bit PCM system, it means, which means n equal to 8 is given. Peak to peak input, which means the peak to peak voltage here is 2 volts they are giving, which means voltage swing. They are assuming the voltage swing to be 2 volts. So here they are giving us the information of voltage swing. If voltage swing is given, yeah, fine, voltage swing is given. So SQNR for an input of 0.5 cos omega t. So they are giving an input which is 0.5 cos omega mt. If this is the input, what is the voltage swing of the input? Voltage swing of the input is only 1 volt, because highest voltage is 0.5, lowest voltage is minus 0.5. And the difference between highest voltage and lowest voltage is only 1 volt. Here this is a little different question, so you have to be careful. What is it? How is it different question? The different how is it different is the voltage swing that they are thinking, the peak to peak input to an 8-bit PCM system is 2 volts, which means they are going to design the quantizer based on the voltage swing, right? So they are assuming the voltage swing is 2 volts and they are designing the quantizer. So they are going to design the step size according to this 2 volts only. But they did not give an input which is also having the same voltage swing. This is the difference. The voltage swing that they are assuming and designing the quantizer and the voltage swing of the input that they are giving, it is different. So that's why it's a different problem. So if it is a different problem, you have to go with the basics. You have to go with the derivation. Whatever procedure you have taken for the derivation, same procedure you have to go. So blindly we cannot do it like this. Since it is an 8-bit PCM system, you cannot use 6n plus 6n formula. 8 6 or 48 dB. Something close to 48 dB is the answer. No, that's not correct. Okay. So actually this will be 43.8. Yeah, this is not 47.8. This is 43.8. Right. Since it is 8 dB, 8 6 or 48. Any answer close to 48 is the answer? No. Why is it not an answer? Why is it 49.8 is not correct answer? Because voltage swing that they are assuming and designing the quantizer and voltage swing of the input that they are giving is different. If suppose for example if this was 1 cos omega mt, then voltage swing here it will be 2 volts, and they are designing also with 2 volts, then simply you can use the formula 6n dB, which is 8 6 of 48. This would have been the answer, but that is not the case. The assumption that they are making, the voltage swing that they are assuming and designing the quantizer is 2 volts. The input that they are giving is having a voltage swing of only 1 volt. There is a difference. So that's why we have to go with the basics. So SQNR is equal to signal power by noise power, signal power divided by quantization noise power, which is equal to, what is the signal power is here? Signal is given as 0.5 cos omega mt. So signal power is 0.5 square divided by 2. Okay, divided by, what is the quantization noise power? So quantization noise power we can write it as del square divided by 12, because no information about the message. Okay, they did not say whether it is sinusoidal, when they are designing the quantizer, since it is sinusoidal, you can assume the quantization error to be uniform, and quantization noise power you can use the formula to be del square by 12, because they are talking about some sinusoidal signal, or if they don't give any information about message signal also, then also you can use del square by 12. So what is del value here? Del value is equal to voltage swing divided by 2 power n. What voltage swing we have to use? It's not the voltage swing of the input, it's the voltage swing that they are assuming, which is 2 volts. 2 divided by 2 to the power of n. What is n? 8. So 1 by 2 to the power of 7. So this is equal to 0.5 is 1 by 2. 1 by 2 whole square is 1 by 4. 1 by 4 by 2 is 1 by 8. Divided by del is 1 by 2 power 7 whole square by 12. So this is equal to 12 into the numerator divided by 8 into 2 to the power of 14. So 12 by 8 is like 3 by 2 into 2 to the power of 14. Yes, we got the answer, but the answer will always, generally when they are talking about SQNR, the options will be in dB scale only, right? So if you convert this into dB scale, SQNR is equal to 10 log. If you apply for this, 10 log 3 by 2, we have seen in the previous derivation also, it is 1.8 dB, plus 10 log 2 power 14 is 14 times 3, which is 14 3s of 42 dB. You can apply using calculator also. This 42 dB, so it will become 43.8 dB. But by looking immediately at it, we will say the answer as 49.8 dB. But that's not correct answer, because there is a difference here. There is a trick here. You have to observe that. So the answer is 43.8 dB. This is the answer. So whenever the question is little different from what assumptions we are making and deriving, then you have to go with this basic procedure. Just follow this procedure. Whenever the question is different, you'll get the perfect answer. Right? So these are the questions, little tricky questions possible on quantization. All the other questions are based on simple formulas only. Right? Now, so this is what I wanted to share today in quantization. So I want to discuss the tricky questions. Fine. So let me share something with you. Right. So this is my introduction. So I've done my master's from IIT Madras. So I've cracked GATE exam twice. So with these ranks, so I used to teach for MEDC, Ace Academy, and Engineer Circle. For the last 8 years, I was teaching for GATE exam, and this is my expertise. I teach 2 subjects: signals and systems and communication systems. And right now, I'm teaching on Unacademy Plus. I'm teaching live classes every day. So every day I teach from 9 to 10, 9 to 11. Every day morning 9 to 11 I teach. So apart from normal classes, regular classes, I take some special classes also on Unacademy. Special classes can be attended by anyone. If you want to attend the special classes, you just come on to Unacademy platform, and you just follow my page. If you can follow my page on Unacademy, then you'll get updates. Whenever I take special classes, you'll get the updates. And whatever courses I'm taking, whenever I'm taking classes, you'll get the updates. You can follow me for more updates on these 2 subjects. I'll be taking these 2 subjects, signals and systems and communication systems. I'll be taking live classes. Right. So I'm dividing the total subject into 4 parts: analog communication, digital communication, random variables and random process, and noise analysis in communication. Total communication subject I'm dividing into 4 different courses, because there are 4 different courses in your semester exams. So that's why I've divided it into 4 parts. So analog communication courses I've already taken on Unacademy platform. And right now digital communication course I'm taking right now. So if you are interested, you can attend the digital communication course on Unacademy platform. So the next course will be start next course will start in another 2 weeks. That course will be random variables and random process, and this is my expertise. I teach this topic very well, beautifully well, and this topic has a lot of weightage in GATE exam and engineering services exam as well. And this is a little tricky topic, and this is very interesting topic also. And after this topic, we'll talk about noise analysis in communication. And after this course, I'll start the signals and system course. So if you have not subscribed for Unacademy, you can attend the free classes that I'm going to take. And if you can take subscription, then you can attend all my classes unlimitedly, which means you can come and attend my live classes, as well as you can come and attend the recorded session also. If you are not able to attend the live class, you can go through the recordings any number of times that you want. Right? If at all you are interested to subscribe for Unacademy Plus, then you can use my code. This is my code. You can use this code for 10% discount. You'll get 10% discount if you use this code. Next, so why you should take subscription on Unacademy platform? Because you will have unlimited. You can use you can view the videos unlimited number of times. You can listen to live classes, as well as you can listen to recorded sessions also. And the most important reason why you should subscribe for Unacademy Plus is because of the fees. So it's a very economical and very affordable fees. So this is the one very important reason why you should subscribe for Unacademy Plus. So if you are having means any confusion or doubts how this platform will be, how the experience will be, you just try it for 1 month, and then you can extend your subscription for many months. So I would suggest you take the subscription for at least 6 months, because in 6 months you can complete all the subjects, and you can listen to all the subjects multiple times also if you wish. And the fees, if you observe, it's very less, very economical. So the places I used to teach earlier, like Engineer Circle and MEDICE and Ace Academy, they charge a fees of around 60-70,000. Sometime in MEDICE it is 80,000. So here the price is like 1/4 of it, and still you can get to listen to the similar level of people who have the same expertise as MEDICE and so on, yeah, at a very less price. And one more thing is, you don't need to travel to classes. You can sit at home and you can listen to the classes whenever you are comfortable to listen to. So it's a huge advantage, guys. If you have not taken if you have not taken the subscription, then definitely, so this is a very extraordinary, this is an extraordinary platform, and it deserves a subscription. If you take the subscription, you're definitely going to get benefited. So just believe me, you're definitely going to have a lot of advantage over other students if you have a subscription, right? So that's it, guys, from my side. So follow me on my page for updates from my side. So if you have any questions, there is my Facebook page. I'll show you my Facebook page also here. So I'll show you my Facebook page. Yeah, this is my Facebook page. If you are having any questions, you can ask me on Unacademy platform, or you can post on this page also. On this page also you can post the questions. Yeah, I'll be replying to those, any questions on my subjects, signals and systems or communication systems. Any questions you can post on this page. I'll be happy to reply you. Okay, right, guys, that's it from my side. Thank you for attending the class. Yes, have a great day. Good night.